Good afternoon. So today I'll be telling you about Maliciously Circuit-Private FHE. So the motivation is non-interactive client-server computation. So client has some input, and it wants to offload it to the server to do the computation. So it sends an encryption of X, and server does fully homomorphic encryption, computes some program f of X, program 1 on this ciphertext, program 2 sends it back to the client, and client decrypts. So typically, this program is big and the input is small, and the goal of FHE is to do the work of the client as small as possible. And often important is to also disclose as little information about the program P as possible, and that's what this talk is going to be about. So how can we ensure privacy of P? Well, on a first glance, if I send something on fully homomorphic encryption and the answer is small, how much information could really be leaked about P? But the client could, for example, ask, is server executing program 1 or program 2? Which one is it? And in particular, what client can do is do something fairly nasty. He can send public key and C, which is a complete garbage, which is not public key for fully homomorphic encryption and not ciphertext for fully homomorphic encryption, but something completely fictitious, with the sole purpose is for the server to execute it thinking it's legitimate public key for fully homomorphic encryption and legitimate ciphertext, and give back some answer such that the client will be able to tell if from this answer if the server is executing program 1 or program 2, okay? And so what can I tell from the evaluation function of a fully homomorphic encryption is something that the standard fully homomorphic encryption doesn't address. Okay, so in particular, what I want to tell you today is how can we guarantee privacy of P if both the ciphertext and the public key that the client sends to the server is maliciously prepared. Okay, so just a reminder, the way fully homomorphic encryption, or in general homomorphic encryptions work, is you have a key generation, you have key generation, you have an encryption gadget, and then evaluation gadget, and this evaluation gadget for different homomorphisms evaluates different programs in some class C. And then you decrypt. Okay, so we all know how this works, but this definition doesn't talk about circuit privacy. And so, it supports circuits. There are, of course, other models of computations, but that's fairly general. It's been, introduced by Gentry with many follow-up works. And the answer is very compact. The definition does not include circuit privacy. So this talk constructs a compact, maliciously circuit-private FHE. So let me remind you how you define these things. The first definition comes from Ishai Paskin 07 paper. They basically say like this. So consider this encryption for some homomorphic encryption scheme. It produces a ciphertext. Then there is a homomorphic evaluation that takes program in some class and outputs it. And there is a simulator that given the output of this program on input X could basically create something which is indistinguishable from the output of the simulator. That's semi-honest circuit privacy. And Ishai and Paskin also defined what it means to be malicious. So it's efficient simulation holds against semi-honest encryptors. And it's basically a la computational indistinguishability. They also defined malicious circuit privacy, which is a little bit trickier. So let me walk you through this definition. So there is a ciphertext and public key that God knows how the user dream up. And you have to say, well, we insist that our fully homomorphic encryption, encryption in general, somehow given public key, any public key, even complete garbage, and any ciphertext defines this unique X star, which may not be even efficiently computable, but somehow, by definition of our FHE, it has to be unique for every even garbage public key in the ciphertext. And then there is a simulator that, given this evaluation P on this X star, can output something which is indistinguishable here. This definition is inefficient simulation and holds against malicious encryptors by statistical indistinguishability. So this equality holds not just with respect to the computational, but also information theoretic, but it's an incomparable notion. Simulator is inefficient, but so is the adversary. Okay? So that's the definition. And what they showed seems inherent for various technical reasons. So malicious setting, why is it hard? A straightforward approach will be, look, we have fully homomorphic encryption. So if we have fully homomorphic encryption, we could somehow homomorphically check that both the public key and the ciphertext are well formed, and if not, output bottom. Unfortunately, not efficient for all known FHE schemes. It sort of works for some weakly homomorphic encryptions that like over group structure, like Al-Gamal. Of course, you can say, look, if we have public key infrastructure, if we have CRS, we can give NIZK, where the user, when he supplies the public key and the ciphertext, immediately gives us non-interactive zero-knowledge proof that everything is set up correctly. But we don't allow setup. We want to say pure FHE, public key, the user gives public key, gives X, and he doesn't rely on a trusted third party. Otherwise, the problem is solved. So the secondary kind of delicate issue is that it may fail for rare public keys in the ciphertext. There are some examples where this could be done. So what was done before? Well, what was done before is we could sort of do it for limited class of functions. So in particular, the work of Ishai and Paskin showed how to do things for branching programs based on Damgard-Jurek, basically based on Payet. And this, we are going to use this as a building block and try to push it all the way to the fully homomorphic encryption. OK, so we use the same definition as Ishai-Paskin. We'll devise a clean general framework for transforming fully homomorphic encryption without circuit privacy into circuit-private FHE and demonstrate instantiations from the literature. Pretty much everything will be done black box, so more or less all the constructions will go through. OK, generalized, and the interesting part is the generalized bootstrapping gadget. So let me tell you kind of a high-level idea, and then the implementation is a little bit tricky. But what do we want to do? We basically want to start with this naive idea of somehow taking homomorphic encryption A, which is typically like fully homomorphic encryption, and has the goodness of the answer is very compact, and somehow start with, say, Ishai and Paskin of weakly homomorphic encryption, but which is circuit private, and somehow combine it together in order to build the best of both worlds. Okay, so we'll get two cryptosystems. We'll start with FHE A with weakly homomorphic or somewhat homomorphic encryption B, which has some properties, and then bootstrap it. And surprisingly, we'll have to do it like 3 times to get our result, and you'll see why. OK, so let's get started. Here's our framework. Step 1, transform compact FHE with no circuit privacy into compact FHE with semi-honest circuit privacy. That's fairly easy. Then we'll show how to take the gadget that we construct out of step 1 and use it as a new part A to construct FHE with semi-honest circuit privacy for somewhat compact FHE, but now with malicious circuit privacy. And then we'll take the gadget that we get out of it and use it again to build the final gadget. OK, so let's go through all the steps. So the first step is you start compact FHE without any circuit privacy. So if I give you a public key and a ciphertext, which are garbage, I could be able to tell when you evaluate on it if you're executing program 1 or program 2. And I'll also start with this program B, which has no compactness, but which has somewhat homomorphic. In what sense? This somewhat homomorphic encryption scheme is enough to decrypt to run the decryption algorithm of encryption A. And now what we'll get from this is, and B also will have weak circuit privacy, and from this we'll get semi-honest circuit privacy of this combined step C. So how would you do it? Let me just go immediately to the construction. So it's similar to the previous work. So you start, here's my public key. You have public key of A, which is fully homomorphic, public key of B, which is somewhat homomorphic, but weakly circuit private. And what you do is you also encrypt the secret key of A and the public key of B. Okay, and your decryption key is just encryption B of key. And to encrypt any bit B under the public key, under this public key, you encrypt it under A, you encrypt this bit under A. And how do you now evaluate this gadget? First, what you do is you take your program P under, say, fully homomorphic encryption, a circuit, and you evaluate it on the ciphertext. And you get this output A of A. This could be garbage because this is not circuit private. But then what you do is you decrypt this A using W. Remember that W is the encryption of B and A homomorphically within B, because you have within B an encryption of a decryption of A, homomorphically within B, and you output this output. And notice that when you do this, if this ciphertext, even if it receives as an input as a garbage, produces something well-defined, or then we get a little bit of a circuit privacy, right? So that's the idea. So decrypt, and now so the result, so we get this output, and the decryption is just we decrypt this output. And sort of a validity sketch is what I already told you. Individual privacy holds because secret key A provides encrypted under secret key B, and semi-honest circuit privacy holds by perfect correctness of A and semi-honest correctness of B. You can get rid of this perfect correctness later. Compactness is preserved because when you do this big computation on A, you run fully homomorphic encryption, so the answer is short. Okay, and you can instantiate it in various ways that I don't want to get into. Why does it fail in a malicious case? Even if B is maliciously circuit-private, and remember B is just honest but curious circuit-private, a malformed ciphertext that comes out from A could reveal some forbidden bit about the program that it's executing, right? Because it could be some crazy malformed public key for this public, the first encryption scheme that somehow encrypts 0 if it's a program 1 and encrypts 1 if a program 2, because the public key is not well formed, the ciphertext is not well formed. And then no matter what you do, even if you decrypt correctly, it leaks information. Okay, so what is the idea? The idea is to say, okay, let's take the previous gadget and somehow homomorphically verify that both the secret key of A, public key of A, is properly generated, and that the ciphertext is also properly generated, right? Because everything could be done homomorphically. Maybe we can supply randomness. We supply all the information about the key generation. And before we start evaluating it, we can somehow homomorphically check that both the public key and the ciphertext are well formed. OK, so let's do this. So the key generation is as in step 1. Evaluation does evaluation of this program on A. And what we do here is also we supply some verification information that guarantees that homomorphically under B we can verify that both public key under A and the ciphertext are well formed. But wait a minute. This may not be a very short, the key generation could be a very long program. An encryption need not be in NC1. So we somehow say, okay, we can homomorphically verify it, but only provided that B can support the homomorphic verification of a public key generation and the encryption of A, which of course varies from scheme to scheme, so we seem to be stuck. So that's one problem, that this is now not compact, because B now has to be very powerful. And so and it's also not completely compact, because now verification of A is polynomial in NK. But of course, if verification of both an encryption and key generation is in NC1, because we started with B that can support NC1, we would be done. But then you have to make all sorts of special assumptions. We want to go all the way and not assume anything. So, OK, so you can argue that this is malicious circuit private, but not compact. What is the idea? The idea is, well, if you somehow can, within B, check that both the public key and the ciphertext are well formed, then the output is valid, just by the construction. On the other hand, if it fails this homomorphic verification of A and B, then you output 0, and again, nothing is revealed about the program that the computer is running, right? So you can instantiate it in various ways. But the question is, right, if both the key generation and the encryption is not in NC1, we seem to be stuck. Because how do we homomorphically verify these things if B cannot support it? And the idea is you do it again by a clever kind of a bootstrapping trick. And here's a trick. The picture looks sort of the same, but it's very different. We'll start with a maliciously circuit-private FHE, which has no compactness. But the component B, we will now say, we will use any component B, which is not necessarily circuit private. And this reverses kind of the roles of A and B. And what is the idea? If we start with a fully homomorphic encryption, which is circuit private, what does it mean? It means that no matter what public key and a ciphertext you feed into the evaluation thing, the output will be well-defined, independent of each program you're running. So then when you decrypt it using compact FHE, which has no circuit privacy, it doesn't matter, because this is already well-defined. And so now, because you reverse the roles, you can actually, and so now you can have maliciously circuit-private FHE without compactness, and then decrypt it homomorphically without any circuit privacy, but because the result is already circuit private, when you decrypt it homomorphically again, it doesn't leak information. And that's the main trick that kind of puts everything together. So that's how you compactize, if there is such a word. Maliciously circuit-private FHE, no compactness. You get compact, somewhat homomorphic encryption B without circuit privacy. And now we are done. So compact in maliciously circuit-private FHE C. OK, so analysis exactly as in step 1, compactness via compactness of B. And circuit privacy, that's the main kind of a punchline. By circuit privacy of A, circuit privacy of B indeed is not needed. We were willing to output A as it is, right? So nothing is leaked. OK. So putting things together, we get the following theorem. Assume A is compact, non-leveled FHE with perfect correctness. Assume also 1 out of 2 homomorphic encryption, somewhat homomorphic encryption with malicious circuit privacy exists. Then there exists a compact maliciously circuit private fully homomorphic encryption. So possible instantiations basically take any FHE from the literature, more or less, and we can turn it into circuit-private FHE. And conclusions, also in the paper, thanks to one of the anonymous reviewers, one of your anonymous reviewers asked, can you do so-called I-hope FHE, which is circuit-private? And we work on it, and you can do it as well. And it's also very modular. You don't need any specific assumptions. So that's in the paper that we just uploaded on ePrint. What other properties of homomorphic encryption can be combined using this generalized bootstrapping gadget, right? So it's basically taking Gentry's original idea and doing it like 3 different times in 3 different ways and getting fully circuit-private FHE. What we've shown is circuit privacy, compactness, I hope, but I'm sure there's other things that you can do, in this way, so what else? And security definition, the biggest drawback is that our definition, the simulator is not efficient, right? Both the simulator and the adversary is not efficient. It's inherent also in Ishai Paskin. Can we make it efficient? That's a great open question. I have no idea how to do it. And that's it. I ran out of time.
Thank you, Rafi.